Welcome back to the ChemDoctor, and this video is going to be directed at the temperature effects of Le Chatelier's principle. Now, I have produced 5 videos that deal with Le Chatelier's principle, and after looking at the 5 videos, I've decided that I need a 6th video that's specifically going to address the issue of the effect of temperature changes on the equilibrium constant. In order to be efficient, let's just dive right into this. So on the screen I have 2 chemical reactions. The one on the left is an exothermic reaction. You can see I've provided the thermodynamic data. So the delta H for the reaction on the left is minus 93,000 joules. And the reaction on the right is endothermic, where delta H is a positive 197,000 joules. Now, you'll remember that basically Le Chatelier's principle deals with 3 ways in which we can manipulate an equilibrium position of a chemical reaction, and then that reaction will respond to that alteration by coming back to equilibrium. And there are 3 ways that we can disrupt the equilibrium of a reaction so that it responds to that disruption. The first is through changing the concentration of one of the reactants or the products, or all the reactants and the products of a reaction, and then the reaction will respond to that by shifting and either reacting with a movement to the right or a movement to the left in order to come back to equilibrium. You can change the pressure of an equilibrium reaction by manipulating the volume, and when you do that, the reaction is going to respond by shifting left or right in order to reduce the pressure and to reattain equilibrium. And the third way that we can manipulate the equilibrium position of a reaction is by changing the temperature. Now, what I want to point out here is that in the first 2 instances, so where we manipulate the concentration of reactants or products, or where we change the volume of a chemical reaction that causes a change in pressure, these 2 alterations do not have any effect on the actual value of K. So you need to remember that an equilibrium constant K, so if we focus for a minute on the reaction on the left here, this K value, which for this reaction is about 9 times 10 to the 5th, this is a magnitude number that tells us at equilibrium what to expect for the ratio of products to reactants. And for the reaction on the left, at 298 Kelvin, we expect at equilibrium that there is going to be a large ratio of products versus reactants for this particular chemical reaction, and hence the number that we have for the equilibrium constant is large. Now, if we were to manipulate this equilibrium, like let's say that we dumped in a bunch of reactants into this reaction vessel, what's going to happen is the reaction is going to shift to the right. So when we dumped in the reactants, what that did to this ratio was it perturbed it. It changed it away from what its normal equilibrium ratio is, so that the concentrations of the products and the reactants were out of proportion. So when this reaction shifts to the right in order to make more product, what's actually going on is that the ratio basically is shifting around to re-equal this number, the number which is 9 times 10 to the 5th. So the equilibrium constant itself, in terms of Le Chatelier's principle, when we either alter the equilibrium position of a reaction by manipulating concentration or by causing a pressure change due to a volume change in the reaction, has no effect on the actual K value. The reason I want to do this video is because the effects that you see for temperature change are distinct and completely different. Because if we manipulate the temperature of either an exothermic or an endothermic reaction, what you're doing is actually manipulating the value of K. So you're actually completely changing this equilibrium position to a new value. All right, and we need to address that issue here, or at least the viewer needs to make sure that they understand that when you change the temperature of a chemical reaction, you actually are changing the value of K, and I want to show you how that happens here. So as we get started, let me shift over here to the reaction on the right, and what I want to do is just address its equilibrium constant. We see this reaction, which is done also at 298 Kelvin. So both reactions are done at the thermodynamic standard state. Notice that its equilibrium constant is 1.3 times 10 to the minus 25th. So in this equilibrium, the reactants are present in a much higher concentration than the products. This is in distinction to the reaction over here on the left, which has exactly the opposite thermodynamics. All right, so you'll notice that when you look at the delta G for the reaction on the left, it's negative and it's a fairly large magnitude number, whereas the reaction on the right has a relatively large delta G naught and it's a positive number. All right, so hopefully you've had some thermodynamics before this, but what we're looking at here are two different reactions as far as the thermodynamics go. And it's important for the student to realize that the thermodynamics are what in fact determine this magnitude number, which is K. And the way that happens is that, well, let me just take you through it. So the delta G, and this is going to be true for both reactions, so maybe what I'll do is I'll put this in the middle over here. So delta G naught, this value, which controls the equilibrium positions of both of these reactions, is equal to the sum of delta H naught minus T delta S naught, right? The delta H naught being the enthalpy of the reaction and the delta S naught being the entropy. The delta H is a reference to the difference in potential energy between the bonds of the reactants and the products. And the delta S naught tells us about the way the order versus disorder is changing over the course of the reaction. Now, the thing about delta G that you need to know is that the delta H and the delta S are constant over a given range of temperatures. So both of these values remain constant no matter what temperature we're at. However, delta G naught is strongly dependent on temperature. So strongly dependent on temperature. All right, and you can see the reason why is right in front of us in the equation, because here's the temperature right here. And going back, the delta H is constant over temperature range, the delta S is constant over temperature range, but this value T can change depending on what the conditions of the reaction are at. So that means that this value, the delta G, is going to be changing depending on what the temperature is. And then we can ask, okay, so that's really great for the delta G, but how is this related to this equilibrium constant? And so this is how that happens. So the delta G is also equal to minus RT ln of K. So here you can see that this value delta G is also equal to this quantity. So the delta G essentially is what controls the magnitude of the K value. So what I want to do to show you what's going to happen here is we're going to take both of these reactions and we're going to increase the temperatures fourfold. So we're starting at 298 Kelvin for both reactions. I've already given you the equilibrium constant in both cases. One reaction is endothermic and the other reaction is strongly exothermic. And what we're going to do is change the temperature of both reactions, an exothermic reaction and an endothermic reaction, to 1192 Kelvin. So this essentially is a four-fold temperature increase. Also, I need to mention, remember that when we're talking about Kelvin, this is absolute temperature. So this is not the same thing as doubling Celsius. All right, we're doubling Kelvin temperature here, and it's a fourfold increase. Now, here's the thing that the viewer needs to see, and I don't want to go through the derivation of this because there's literally not time to do it. I would end up having to lecture for something like an hour or something if I wanted to go through and show all the derivations, how this works. So what I'm going to do is show you the relationship between two different equilibrium constants versus change in temperature. And what I would recommend is that you sit down later and do the derivations yourself. And basically how it works is, I'll show you the setup. All right, since delta G naught is equal to delta H naught minus T delta S naught, and it's also equal to minus RT ln of K, we can set up the following relationship where minus RT ln of K is equal to delta H naught minus T delta S naught. All right, and we can stipulate that this is going to be at temperature 1. We're going to have another expression for the temperature at T2. All right, and we can show that this way. So we have one expression for each of the different temperatures. When we combine both of these by taking the difference of both sides of the equation, we get a new equation which looks like this. So it's going to be ln of K2, this will be the equilibrium constant at our new temperature, whatever it is, over the equilibrium constant at temperature 1. And this is going to be equal to negative delta H naught over R times 1 over T2 minus 1 over T1. The delta S naughts, and you'll see when you do this, they end up canceling out. So this is our final equation right now. So now, if we take a look, first we'll deal with the reaction on the left, and notice that at 298 Kelvin, that K is a huge number, that the reaction vessel is going to hold way more products after the reaction comes to equilibrium than reactants. So if we calculate the new equilibrium constant at where T is equal to 1192 Kelvin, the equilibrium constant that we get, K2, is actually equal to 6.55 times 10 to the minus 7th. Now when I run these calculations, and I use this equation and run these calculations, I tend to carry all my numbers out. So you may not get exactly the same number as me, but you should certainly get a number that's in the same magnitude range as this. And what you should notice that's so striking about this is to compare the equilibrium expression, the equilibrium K constants, because at 298 this value is 9.1 times 10 to the 5th. It's a huge equilibrium constant. But by increasing the temperature of an exothermic reaction, look what's happened to the equilibrium constant. We've totally flipped to the other side, where now we're in a situation where the reactants are in a much higher concentration range at equilibrium than the products. So this was why in the previous videos I said what you're going to need to do if you want to shift equilibrium to the right to favor the products of an exothermic reaction, you need to cool the reaction. So what I would suggest the viewer does is do what I did here simply, and that is to take and decrease the temperature of this reaction, say fourfold. Figure out what that temperature value is going to be and calculate your K. And what you should see is that the K is going to be significantly larger than this value here. Now switching to the other side, I want to do the same thing for this reaction. So we're going to do a fourfold increase in temperature, and this is an endothermic reaction. And what I said in the videos where we dealt with temperature changes for an endothermic reaction is you actually want to heat that reaction. So let's see what happens when we take our temperature to 1192 Kelvin. Alright, and we use the same relationship here. We solve for the new equilibrium constant, and what we get here is a new value where our K2 is going to be equal to approximately 10. All right, now check this out. At 298, we started with an equilibrium constant, which is 1.3 times 10 to the minus 25th. This is really a teeny equilibrium constant. Like I said before, at 298 Kelvin, the concentration of reactants at equilibrium far outpaces the amount of products that you're going to find in that reaction mixture. But by increasing the temperature, the absolute temperature from 298 to 1192 Kelvin, we go to an equilibrium constant which is equal to approximately 10. All right, which means that at equilibrium at 1192 now, the amount of products is going to substantially outpace the amount of the reactants. All right, and to finish with this presentation, so here's the take-home message. The take-home message is with Le Chatelier's principle and temperature, what you need to realize is that if you change the temperature of a chemical reaction, you are in fact changing the value of the equilibrium constant. This is not a simple matter that you're just manipulating the proportionality of the equilibrium expression, and then the system is going to shift this way and that to come back to the original K value. You are in fact changing the K value and generating a completely different equilibrium position that now that reaction will respond to. So in other words, if once we've changed the temperature of the reaction and we've come to a new equilibrium value, then if we turn around and we start manipulating Le Chatelier's principle for concentration and pressure values, that system is going to respond by coming back to the new equilibrium constant unless you readjust the temperature back to its original value at 298 Kelvin. And with that, I'm going to go ahead and close this video.